Good afternoon to all the members of INAE and other attendees. Today's topic, as you see on the screen, is decarbonization of cement, steel, and power sector. Decarbonization is very important, but when we think about decarbonization, the first thing that comes to mind is energy generation or the power sector. However, there are several other sectors of economy that need decarbonization, and that includes transport, cement, steel, fertilizer, agriculture, and so on. Within transport, there are several subsectors such as rail, road, shipping, and aviation. And many of these sectors or subsectors are hard to abate and need a lot of research and development efforts. For many industrial sectors, there is a need not only for alternate fuels, but also for alternate raw materials. Often we abbreviate this as AFR, that is alternate fuels and raw materials. The aviation and agriculture sectors are regularly pointed as villains of the climate crisis, but cement sector is a more significant source of carbon dioxide emissions. Cement production contributes to 8% of all global CO2 emissions. That's more than most countries' total CO2 output, according to think tank Chatham House, and more than double the emissions from the airline industry. But there are signs that change is coming. The same is the case with the steel, and that brings me to today's talk. The speaker today is going to tell us about decarbonizing these hard to abate sectors. Introducing the speaker for today's talk, let me inform all of you that we are going to have INAE conclave on 26th and 27th October. And on 26th October, Dr. Sanak Mishra, the past president of our academy, will be speaking on decarbonizing the steel sector, and Shri Mahendra Singhi from Dalmia Cement will be speaking about decarbonization of the cement sector. So before I introduce the speaker, let me add that hydrogen is a promising substitute for carbon for providing energy as well as a raw material or a molecule. Without taking much further time, let me introduce the speaker, who has Mr. Ulhas Parlikar. He has over 36 years of experience in various segments of business, research and development, technology development, scale-up, product design and engineering, project management, business development, consultancy, marketing, strategic planning, and so on. He graduated in chemical engineering from Osmania University, went on to receive MTech in chemical engineering from IIT Madras. He also did a program at IMD Switzerland on senior management and senior leadership training. He was working with ACC. He built a large Geocycle business as deputy head of Geocycle India. Spearheaded co-processing initiative in the country, established it as a large business model, implemented advocacy through CII for the Confederation of Indian Industries to include co-processing in Indian policy framework, and served as an expert member on several government committees. After retirement in 2008, he continues to be active and provides consultancy internationally as well as within the country, and has published his experiences in various journals. So with this short introduction, I invite Mr. Ulhas Parlikar to deliver his talk. Parlikar sir, please, all yours.
Thank you, Professor Grover. It's indeed my pleasure. It's indeed my pleasure to be with INAE colleagues and share some of the learnings that I have had in the course of trying to reduce the CO2 emissions from the cement industry. That also helped me to work in the area of waste management and see, whether we can do something better and more efficient in the areas of waste management which is happening in our country. So I will straight away, start with the presentation. I will share my PowerPoint presentation first. I'm putting it on the full screen mode. Yes. I think you are able to see it, right?
Yes.
Okay. So, ladies and gentlemen, I'm going to discuss something related to decarbonization in the cement, steel, and power sector. At the outset, I would like to say that, the major effort in terms of decarbonization has happened in the cement sector, and the steel and power sector are following through. As Professor Grover said, cement is a very, very carbon intensive industry, and it releases large amount of carbon dioxide. There are varying numbers, but anywhere from 5 to 7% of the total emission which happen globally from the industry sector. But the industry actually has taken a lot of efforts and initiatives to reduce this emission and move towards a low carbon technology. In fact, the Indian cement industry worked with the International Energy Association and World Business Council for Sustainable Development to chart out a roadmap, a low technology roadmap, low carbon technology roadmap for the Indian cement industry in the year 2011 to 2013. During that time, I had the opportunity of being associated with that as an author. And that's how I think the Indian the cement industry has been pursuing the decarbonization agenda in the country. Globally also, this particular agenda is very intensely followed up. Now, the reason for that is these numbers, if you see them. The total energy related CO2 emissions in 2018, as per IEA, International Energy Association, were about 33 gigatons. Out of that, cement was 2.4 gigatons, steel was 2.6 gigatons, and thermal power was 10.1 gigatons. It's a pretty large number if you look at it. And the industries are very conscious of these particular status. They have understood the impact that these emissions are making on the environment, on the climate, and all these industries are evaluating, exploring, and also charting out plans to ensure that the carbon dioxide emissions, the GHG emissions, would get reduced. The target which has been set by various forums is that we must ensure less than 1.5 degrees centigrade increase in the ambient temperature compared to the pre-industry period. And that is where, everyone is trying to do. We have several countries who have taken up initiatives. They have put them across to the various industry segments, various other business segments, and cement, steel, and power are no exceptions to that. They are putting best efforts to reduce the CO2 emissions to the required levels. There are several industries today who have set their goal to achieve net CO2 status, net zero CO2 status in a defined timeline. So with this particular, sort of a background, I would like to take these deliberations forward as to what are the major levers available for the industry, particularly the steel, cement, and power industries, to reduce the carbon dioxide emissions, or so to say, decarbonize themselves. So the first and most important thing is to improve the resource efficiency in manufacture. So whether it is the raw materials, whether it is the energy, any fossil material which is being utilized, how can we increase the efficiency of that, efficiency of utilization? There are various ways in which leakage of these materials happens in the manufacturing processes. So how can we plug them? How can we improve the efficiency? Something that the industry can do, and industry is exploring and doing also. The second important thing is how to reduce the use of fossil fuels and the raw materials that contribute to CO2 emissions. So for example, all the fuels, fossil fuels, whether they are coal, oil, gas, you name anything, they are the ones which release CO2. So how can I reduce the utilization of fossil fuel is being addressed. And also the materials, because you're mining them and then you are utilizing them, you're actually exploiting the Mother Earth. And that's why you're also adding to the environmental impact. So how can I do that? How can I reduce the utilization? Is another question which is being asked, pursued, plans are being made, and the mission is taken forward. Replacing fossil resources with renewable ones. For example, hydrogen. Because hydrogen, once you combust, it does not release carbon dioxide. The question is, can I produce green hydrogen? So can I produce hydrogen from renewable resources? Can I produce hydrogen from green energy? So that's the question which is being asked. And there are several initiatives which are happening in the industry. Replace fossil fuel-based energy with renewable energy like solar, wind, geothermal, tidal, etc., etc. So towards that also, large amount of investments are happening. If you see in past decade, there has been a lot of development in solar and wind, and I expect that wherever opportunities are there, even geothermal and tidal also will be explored. Converting CO2 to algae and use it as fuel. There are several industries who are exploring this possibility because algae provides this opportunity of converting CO2 into an organic substance, which provides an opportunity to be utilized as fuel. So it becomes a recycling sort of a fuel. So same CO2 keeps on recycling. So you're not adding net CO2 into the environment. Can I do the sequestration of carbon dioxide and convert that into some useful materials, which otherwise would be manufactured from the fossil materials like crude oil? So can I convert CO2 into some chemicals in some technology options? That's another, carbon capture and sequestration or utilization, which is being explored by the industry. And the last and very interesting one is utilizing waste materials as resources in the manufacturing process. The term, the definition there for such an activity is co-processing, which means that you use the natural, normal, conventional materials as resources in manufacturing process. You use waste materials as alternative resources in the manufacturing process. So you use waste materials as fuels and raw materials, as Professor Grover was talking about, as alternative resources in the manufacturing process. And that's the concept of co-processing on which I had opportunity of working substantially in the country, and most of my submission would be in that area because that is most dear and probably I'm more familiar on that subject. So co-processing is basically utilizing waste as resources. And it is based on the principle of industrial ecology. It stands for the usage and disposal of waste materials as raw materials or as a source of energy or both in resource-intensive industries. What are the resource-intensive industries? Now, cement, steel, thermal power, lime industry, refractory industry, glass industry, and industries of that kind. They are highly resource-intensive industries, both raw materials as well as fuel. So, in such industries, there is an opportunity for replacing the natural mineral resources, where we are talking about material recycling, and also fossil fuels such as coal, petroleum, gas, etc., as energy recovery by waste materials. And that is where one of the very important levers of decarbonization rests. And it is a highly developed concept in the cement industry. This concept is also being explored by the other industry segments such as steel and power, but the progress in that direction is rather low. But once I explain to you the opportunity which has been explored by the cement industry, exploited by the cement industry, you will realize what is the potential available for even the steel and cement in the power industry to utilize the same. So in cement manufacture, the waste materials get utilized as alternative resource materials. They could be like industrial wastes, hazardous or non-hazardous. They could be derived out of municipal wastes. It could be RDF, plastic waste, gas generated, biogas generated from the kitchen waste, etc. Then the agricultural waste, non-cattle feed biomasses. So these are the three waste segments which are substantially feasible to be utilized in the cement manufacture as alternative resource materials. Waste materials that get utilized as cementitious materials because they have got properties which are called as pozzolanic properties, with which you can substitute the clinker, which is an intermediate in the manufacture of cement, with these materials. So for example, fly ash, the slag from blast furnace, volcanic ash, or even the red mud, which has a huge potential for utilizing it as a pozzolanic material and replacing clinker in the manufacture of cement. And there are other materials which replace gypsum, like for example, phosphogypsum from fertilizer industry, FGD gypsum from the environmental, or SOx reduction industry or options, and also chemical gypsum, which are produced in the chemical industry. So these are the three different options which are exploited substantially in the cement manufacture in its decarbonization journey. I'll give you some examples, which are very, very interesting in terms of volume and the capability of the cement industry in utilizing waste as resources. In 1950s, there was a fertilizer plant which was being considered to be built by Government of India. And the fertilizer was ammonium sulfate. Now the question is, when you make ammonium sulfate using rock phosphate, sulfuric acid, etc., you also produce calcium carbonate slurry and almost equimolar. Now the question is, if you produce 1 million tons of ammonium sulfate, you will produce almost 1 million ton of calcium carbonate slurry. What will you do with it? So someone said, maybe, cement utilizes calcium carbonate. So why don't we explore whether we can make cement out of this calcium carbonate slurry? And at that time, the Government of India or representatives who were dealing with this project, they approached the cement industry. At that time, it was ACC. And they checked whether it is possible to make cement and whether ACC would be interested in setting up a cement plant for it. ACC did some survey, some evaluation, and then they confirmed, yes, we can. Now, this fertilizer plant was set up in Sindri, and ACC set up a cement plant adjacent to this fertilizer factory. Both these plants, they ran together for more than 35 years. That cement plant stopped producing clinker from calcium carbonate slurry when the ammonium sulfate plant was shut down, because it was not very economical to produce ammonium sulfate. Urea had taken over at that time. Steel plant, we produce the blast furnace, we produce iron in blast furnace, and in the process you also generate slag. Now that slag, it is processed through a granulation technique in water. It develops certain properties which provide this the pozzolanic characteristics to the slag. This technology was developed and implemented again way back in 1960s from the Bhilai steel plant, and a Jamul cement plant of ACC was set up adjacent, about 2-3 kilometers away, and a large amount of blast furnace slag started moving into the cement plant. Fly ash was a major cause of concern during 1980s and 1990s. The government was, trying to understand what to do with this particular fly ash. The fly ash mission was designed. Various applications were identified. Again, cement industry, it found that they can utilize large amount of fly ash. Several initiatives, several research activities, evaluation activities were done. Standards were prepared, and large amount of fly ash started getting utilized in the cement manufacture. Pet coke from the refineries was another example where it has got large amount of sulfur content, almost 8%. Now, such a waste stream, is very difficult to be utilized. However, cement came forward and started utilizing this as a fuel, replacing the coal which was being utilized. Agro waste, which are non-cattle feed, was another example. Several cement plants, wherever there was an opportunity, wherever the material was getting available, it started utilizing that. Then this initiative intensified in last 15 years or so in the country. And then, we started utilizing the municipal derived waste like the RDF produced from the municipal solid waste or produced from the combustible fraction. We call it as segregated combustible fraction. And that RDF started moving and getting utilized in the cement. Industrial hazardous and non-hazardous waste, all kinds of industrial hazardous and non-hazardous waste, whether they belong to schedule 1, 2, 3, doesn't matter. All of them are amenable for utilizing in cement kiln as a resource material, and they have started utilizing this. So if you look at this particular waste scenario, there's a fantastic bond between the cement industry and other industries which are generating waste, and substantial quantity of waste gets utilized in the cement manufacture. When we utilize waste as resources, it actually helps build circular economy. And that's where I think, I'm very, very happy and very proud to be associated with cement industry, because cement industry is pioneer and a leader in utilizing waste as resources. Now the concept is that we have actually exploited our mother earth by way of linear economy, where resources are utilized for manufacturing. The manufactured products are consumed and used, and once their consumption is over, you just discard them as wastes. Same waste, if we are able to recycle it as a resource, that waste does not remain as a waste in the environment, and it finds another economic alternative for its use, and it gets into the business cycle. And that's where cement industry did a lot of work, and that's how I think it facilitated building of this circular economy. The idea of circular economy is to look at zero waste future. And so all R's, whichever are feasible, required, or amenable for implementation in the economy, need to be provided. And cement industry has potential to utilize all these options of recirculation or recycling or recovery, etc., facilitating a zero waste future. When we utilize waste as resources and facilitate circular economy, what are the benefits that one can get as society? So it reduces the required number of landfills. When I started working on this concept way back in 2005, there were many industries who had no option but to send their waste to the landfills. So when we said that, look, if you will give this material to us, we will utilize it as a resource. You will be able to divert that material away from the landfill, and in all probability, we will help you become a landfill-free company. And I'm very proud to say that many companies, many organizations collaborated with us in that journey and achieved this status of being landfill-free. The lesser amount, when it starts moving towards landfill, obviously, the number of landfills required also starts reducing, and that's in the interest of the nation. Pollution caused by dumping also gets reduced, because there's large amount of dumping also which used to happen, which still continues to happen. The same amount, same material, when it starts moving as a resource material, it has a different economic angle, and therefore, it doesn't go towards the pollution path of dumping. The greenhouse gas emission, in cement industry, when we use wastes, so we are actually replacing the fossil fuels. So fossil fuel, the CO2 from fossil fuel is something which is anthropogenic. Basically, it is contributing additionally to the CO2 emissions which are happening. Whereas if we are utilizing waste and replacing them, to a large extent, we are reducing that CO2 impact. Environmental impact of extraction through mining, because a large amount of waste we can utilize as raw materials. You have lime in waste from the paper industry. You have red mud from the aluminum industry. You have steel slags from the steel industry. From the zirconium industry, from the lead industry, from copper industry. There are several, industrial waste which are there, which can be utilized as the input raw materials in the manufacture of cement. So to that extent, you don't have to mine the material from the mother earth. So therefore, the dependence of primary, resource markets gets reduced, and cost of production of cement obviously comes down because of waste utilization. It mitigates the climate change impacts. It conserves the energy and material resources, because 1 ton of coal, if we have replaced by utilizing 1 ton of or whatever quantity of waste, that 1 ton of coal is not required to be mined. So that material remains in the mine and remains forever, so long as we continue to replace and keep replacing the waste for the fossil fuels. And obviously it promotes circular economy. Co-processing, if you look at it, is substantially higher in the waste management hierarchy, because it has status very close to recycling. You have prevention, reduction, reuse, recycling, and co-processing. And then you have waste to energy, incineration, landfill. If you look at co-processing, it provides 100% material recovery and 100% energy recovery. What I mean by that is, once we put waste into the cement kiln as a resource, the ash content in that gets utilized as an input raw material. And the combustible organic portion in that, it gets utilized as energy resource. So once the waste goes inside the cement kiln, it's gone forever. There's no waste at all subsequently to deal with. Compared to the waste to energy, where the energy recovery would be about 27, 20, and if you go for combined cycle, probably more. Whereas material recovery, zero. You still have to send the waste, the ash, whether it is bed ash or fly or the other ash, into the landfills. And then obviously we have the incineration and landfill, which are very, very low in the hierarchy, because they do not provide opportunity of any recycling at all. So the idea of moving towards decarbonization or towards circular economy is to avoid the incineration and landfill as much as possible, obviously to take it to a stage where it is zero. And that's how I think, cement kilns and also the other resource intensive industries that we are going to talk about, they have the potential to do that. Let's look at the cement kiln and its features. I don't know how many of you have seen a cement manufacturing plant. The brown cylinder that you see here is a giant cylinder having a diameter of about 4.5 meters to about 6 meters and length anywhere from about 80 meters to 100 meters. The tower of cyclones that you are seeing there is also very gigantic. It's about 120 to about 180 meter tall, depending on the design factors which are there while building this cement plant. On the right, the gray part that you see is a cooler where the hot clinker is cooled into granules, which are called as the clinkers. The clinker. It's an intermediate product. That clinker you actually then grind with gypsum, and depending on what cement you want to make as PPC or PSC or a composite cement, you may add fly ash, slag, limestone, etc., etc. So that's the cement kiln part of it. The flame that you see there, that has a temperature very close to around 2000 degrees centigrade. Since the length of the cylinder is about 100 meters, the gases get a residence time of about 6 to 10 seconds, depending on the design of that particular equipment. So this, and the end of that particular cylinder, the temperature will be about 1100 degrees centigrade. So 1100 degrees to 2000 degrees, the residence time is about 6 to 10 seconds. That kind of environment, will combust anything and everything that comes into the kiln. Because if you look at the most efficient and hazardous waste incinerator, you need 2 seconds residence time and about 1100 degrees centigrade as the design requirement. This is much, much, much more powerful than that. And then you have these cyclones where the hot gases are going up and the cold material, which consists of limestone powder and iron and silica and alumina in certain proportion, which is called as raw meal, is flowing down, and it is a counter, counter flow sort of a mechanism there. And in the process, the hot gases become cool and the cool raw material becomes hot, and the process of manufacture, is facilitated in that manner. So in this cement kiln, you have option of feeding these waste materials as resources at 3 distinct locations. The first one is called as pre-calciner, which you see on top there. In this pre-calciner, we can feed liquids, we can feed solids, which are coarse particles, and if you have gas also, you can feed them. The one on the left bottom corner, which is called as kiln inlet, there you can feed lump fuels. That means waste materials or fuel materials prepared from waste, which are put in the form of, let's say, a bag or a drum, or even a whole tire, a truck tire, can be directly fed into this kiln, and it rolls inside the kiln, and that gets combusted, and really whatever energy is released is utilized by the process. And then you have the third point, which is called as kiln main burner. This main burner, you can feed liquids or fine solids or the gases. And if you look at waste streams, they can be solids, they can be gases, they can be liquids, and they can be sludges. So all these kind of waste materials are amenable for feeding into the cement kiln, and that's the beauty of the cement kiln that we are talking about. Now, I already told that the flame temperature is more than 1800, it's up to 2000 degrees centigrade, residence time is 6 to 10 seconds, about 1100. And the calciner also has got more than 900 degrees centigrade and somewhere around 5 seconds residence time. So under this condition, when you put any organic combustible material into the kiln, it gets combusted fully. There's a measure which is called as destruction and removal efficiency, DRE. So for the incinerator to be called as the most efficient incinerator, you need 4 nines. That means 99.99% DRE. But there are several kilns, where we have done measurements. They range from 6 nines to even more than 10 nines. So that's the efficiency of combustion which is there in the cement kiln. Now, when you combust the materials, you may end up with sulfur dioxide, hydrogen chloride, hydrogen fluoride, sulfur trioxide, H3PO4, and gases of that kind. Now, most of these acidic gases, they react with the limestone which is coming down, and while coming down, it is getting heated, and it gets calcined into calcium oxide. It's a very fine powder, so it has a very large surface area, and with this high temperature, large surface area, and intense mixing because of this counter current flow of gas and the solids, you get a beautiful interaction and reaction between the acid gases and the raw materials, and therefore no acid gases tends to get released or left out from the cement kiln. So all the acidic gases are taken care, combustion is taken care, and the temperature environment, because it is very high and the gases are cooled in a very particular manner because of the design consideration, there are no possibilities of dioxin and furan formation. All the ash which is present in the waste stream, that ash becomes raw material, because ash normally contains only oxides of metals, calcium or magnesium or silicon, iron, aluminum, etc., etc. So it becomes a composite mix of the cement manufacture. You may have heavy metals. Now, these heavy metals could be, all kinds of heavy metals, could be chromium, mercury, thallium, arsenic, you name them, all these heavy metals. This clinker matrix, then what we talk about, which is getting produced in that brown cylinder, that clinker matrix is a crystalline material. And all these heavy metals, they get embedded into that and they get completely locked up. So there is a capacity for this cement clinker to accept these heavy metals and bind them in a manner that they don't get leached out at all. So even if there are some amount of heavy metals present in the waste streams, it is not a cause of concern at all. Only cause of concern are two. One is the chromium 6, because it is very low labile and it is leachable. So we ensure that chromium 6 is not entering into the cement kiln. And the second one is the mercury, because mercury is volatile. And this mercury has potential to rise and then leave from the stack in a volatile stage. So therefore, we have an input control on this mercury and the chromium. Most of the other heavy metals are easily trapped. So if you look at this particular process of co-processing happening in the cement kiln, there's absolutely no cause of concern on the emission. And this is not a statement that I'm making. There were several demonstrations which were done, and I was a party to that nothing could be found which was abnormal, atrocious from the emission considerations point of view. Now, when I say waste utilization as a resource, there's a very clear distinction between resource and waste. All the photos that you are seeing, except the one on the right corner below, they are all waste streams, and there are no arguments on that. Everybody will say, yes, that is a waste stream only. Whereas when you look at this particular right-hand corner photo, 100% everyone will say that this is a resource material. So what is required to be done is that you have to convert the waste material into a resource material. So you have waste streams which you are seeing on the left side photos. And once you see them, you know that that is a waste material, and obviously that cannot be utilized. Once you send it through a pre-processing facility, which is shown in the middle photograph, and convert that into something which looks like the photo shown on the right side, it becomes a resource material. And what are the technologies which are used for pre-processing? This is called pre-processing step. You have shredding, blending, impregnation, baling, screening, drying, etc., etc. So waste streams do not have any specification. It's like, we tend to say garbage is just garbage. You cannot define any specification for that. Today it is something, tomorrow it is something else. Today it is something, tomorrow it will be completely different one. Whereas when I say resource, today or tomorrow, it's only same material which I'm looking at. So it's a technology intervention which is required to convert this waste material into resource material. And that is the beauty or the hard step of co-processing in all the resource intensive industry. It's not just for cement. So for example, industrial waste, I showed in this particular photograph that all kinds of industrial waste through the processes that I described, you are converting that into a resource which is shown on the right side photos. A very familiar example is the combustible material from municipal solid waste. If you look at the left side photo, I'm sure, again, there can be no arguments. This is a waste material. It cannot be utilized as such. Nobody will even go near it for utilization. But once you look at the photos on the right side, everybody will agree that this is a resource material, and everybody will decide to accept this material as a resource material. So what is that which changes this is a pre-processing facility. And that is something which has to be built for the resource intensive industries to utilize waste and resources. Now, this particular material, on the left side, in cement industry, we coined this term called as SCF, which is segregated combustible fraction. It has got documented even into the government, vocabulary. And the one which is on the right side, we call it as RDF, which is refuse derived fuel. And that also has gone into the vocabulary in the government documents. So earlier, the left side material, which is there, even used to be called as RDF. And there used to be a big question, big argument as to why cement kiln is not accepting RDF from the municipal solid waste. Although cement industry has been claiming to accept RDF as a resource material. And actually this explains what it means for cement industry to call as RDF. And that's how, there have been mindsets, a lot of, interaction, discussions, negotiations on this. And finally, the government worked in working out standards for this RDF. So you have 3 different grades, which is called as grade 1, grade 2, and grade 3 RDF, which can be made from the municipal solid waste derived combustible material in terms of its size, in terms of its chemistry, like ash, moisture, chlorine, sulfur, and calcific value. And also if there are any other constraints which may be there at the cement plant. So this is something which was kind of, documented these are the standards which have been now prescribed by the Ministry of Urban Affairs as a acceptable material for cement kilns. Cement kilns have accepted that this is the material that they have no concern to accept, and the system is now gearing up to produce this kind of RDF from the RDF that I'm showing on this left photograph, which they used to say that has to go to the cement kiln. So that's the state of affairs, and I'm very happy to tell you that today more than 5 lakh tons of segregated combustible fraction is moving to the cement plants for co-processing and replacing the fossil materials. The process is, you have dry and wet segregation. That is the key. If you don't segregate these materials, then you have a big problem, in terms of what kind of material that you will get. So the rules have really brought out a very, very essential requirement of the efficient utilization of resources, that it should be dry and wet. The dry material goes for starting in the MRFs, which is material recycling facilities. You remove the compostable, you remove the recyclable and the inert materials out of that. And then whatever remains, as non-recyclable and combustible material, which is called as segregated combustible fraction, that is sent for pre-processing, and the pre-process facility converts that into RDF, and the RDF is utilizing in the cement kilns. At this point in time, most of this pre-processing is done by the cement industry itself. They have set up several facilities within their cement plants to convert this RDF or even the waste materials from the industries, whether they are hazardous or non-hazardous, and are utilizing them as resources. Is co-processing a proven technology for waste management? So if you look at this particular technology, it is in operation for more than 40 years now globally. There are cement kilns which are operating at 70 or 90% replacement of fossil fuel. That means they are using mostly the waste only as fuel. Only 10% or less than that is the fossil fuel that they are utilizing. In our country, this process has started. The acceptance level have started. So there are cement kilns in the country which have reached a figure of about 25 to 30% replacement. It's an approved technology by Basel Convention for disposal of all kinds of hazardous and other wastes. It is recommended for destruction of the persistent organic pollutants and also ozone depleting substances under Stockholm Convention. In fact, we demonstrated in ACC one of our plants that the ozone depleting substances, particularly the CFCs and HFCs, and we demonstrated that they can be disposed. We disposed a huge stock which was there in the country and which was causing a large embarrassment for the country in terms of holding that stock of ozone depleting substances. And we destructed them. And while doing that, we carried out the entire measurements of the emissions, the process, as per the international standards, not just from our Indian perspective, but we also involved the scientists from the Stockholm Convention, scientists or the research facilities or the analytical facilities from Australia and Belgium, so that the questions of operations carried out during these destructions are not questioned subsequently. And it was a fairly very successful kind of a trial which was published in all kinds of the very reputed journals, and it is one of the very well accepted publication for the disposal of ozone depleting substances today. This particular co-processing is a sustainable solution for management of hazardous and non-hazardous waste from all industrial, municipal and agricultural sector, and many developed and developing countries have adopted that. So there's a clear recognition of this particular technology. Now, is it proven in India? In fact, in India, we did more than 90 trials to demonstrate that. And it is very interesting to note that every trial costs something like 10 lakh rupees. So it was more than about 9 crore of rupees which went into the investigation process. All these trials were confirmed as that they do not have any impact on the emissions, process or product quality of cement. Today, India is 5th largest consumer of waste as resources in the cement manufacture. We utilize about 5 lakh tons of SCF, as I told you. We also utilize a large amount of industrial and other waste as AFRs. Today, that number is about 4 million tons of waste we are utilizing as fuels and resources in cement manufacture. We also utilize about 0.5 million tons per annum of red mud as an iron substitute in cement manufacture. 50 million tons of fly ash and more than 10 million tons of slag are utilized. Large amount of phosphogypsum, chemical gypsum, FGD gypsum are also utilized in the cement manufacture. So it's a very interesting, technology where wastes are getting utilized and fully demonstrated. Is it a recognized sustainable solution for management of waste in Indian regulation? Yes, it is. Co-processing earlier was recognized in 2008, but there were a lot of riders. Every waste stream that you want to co-process, you must demonstrate the trial for that. And that's why we did 90 trials. And co-processing now in 2016 has been incorporated into the 2016 hazardous waste, plastic waste and solid waste management rule. There is no trial required anymore. It has been accepted as a very clean technology for managing or utilizing waste. Today, waste can be transported across the states if it is sent for co-processing or recycling. Earlier, there was a ban, complete ban on sending hazardous or other waste across the states. Relevant guidelines have been published by CPCB for pre-processing and co-processing of waste. As per solid waste management rule, any manufacturing entity utilizing fossil fuel is obliged to replace 5% of fossil fuel with RDF generated within 100 km of its radius. So that's the recognition which is there for this particular technology, and which waste can be pre and co-processed. All non-recyclable, non-hazardous waste, like for example FMCG waste, shampoos, creams, chocolates, Maggi, all you name them, non-hazardous waste which are date expired, all of them are utilized in the cement kiln. All non-recyclable, hazardous and other waste belonging to hazardous waste belonging to schedule 1, 2 and 3. All non-cattle feed agro waste, whether they are cotton stem, mustard stem, pulse stems, you name them, whatever they are, which are not cattle feed, they are all, utilized in the cement manufacture, apart from, usual bagasse, rice husk and other biomasses. All kinds of expired food and other products, which I already told you. You know, when Maggie was banned in our country, almost every kg of Maggie was sent into the cement kiln as a fuel and raw material source. All kinds of expired FMCG products, whether they are soaps, detergents, shampoos, creams, lipsticks, chocolates, you name them, everything goes into the cement kiln today. Otherwise, it used to come back into the marketplace as a spurious material. SMC, sheet metal compounds and fiber reinforced plastics, where there's no option available for their sustainable management, only landfill used to be the one. The cement kiln has been found as a most appropriate solution for that. So co-processing today can be done without any trial demonstration, etc., because it has attained that recognition as being a sustainable solution. Which waste can be co or pre-processed? There are banned wastes, you know, for pre and co-processing. Radioactive waste, you know, we don't. Asbestos containing waste, explosives and ammunition or weapons, and anatomical hospital waste. These are something which are not acceptable and they are banned in the cement kiln. And there are several safety and other related issues, therefore they are banned. But there are some waste, you know, which as such are banned for co-processing, but if you pre-process them in a particular manner, then they can be utilized. For example, electronic fraction of electrical and electronic waste. Heavy metals, you know, they are mostly heavy metals or other metals, you know, so or rare earth metals. So we don't want to co-process them. You have a better, you know, option for managing them. Whole batteries as an application, you know, all the heavy metal, whatever is there, once lead or bismuth, cadmium or whatever is there, you remove that. Rest, what remains, if it cannot be recycled in any manner, that can be utilized in cement. And also waste of unknown, unpredictable composition, including unsorted municipal waste. So these, if you process them material, like I showed you how the SCF is converted into RDF, that kind of waste material then can certainly be utilized. You know, if you look at decarbonization status, you know, if you produce OPC, which is the conventional cement called ordinary Portland cement, you know, cement industry said that I want to reduce. So they started looking at other options of utilizing waste material. So when you put fly ash, and if you are allowed 35% fly ash into that, you know, you can reduce from 800 to something like 500 kgs per ton of cement. Instead of fly ash, if you decide to use slag, which can be incorporated as per standard up to 60%, this gets reduced to something like 300, you know, kg per ton of cement. And in a cement, which is where you are manufacturing the PSC, which is Portland slag cement, if you utilize fossil, if you replace fossil fuel with AFR, you know, it can go to something like 200. So from 800 to 200, 1/4, you know, is the status of GHG emission, which happens by way of this decarbonization journey. So there is a huge development which has happened in the cement sector, and that's how a large amount of CO2 reduction which is happening, and it's progressing substantially ahead. There is when I come to the steel sector now, you know, there's a steel plant called Voest-Alpine in Austria. This also utilizes waste as resources, and almost 100% it utilizes only waste materials, and very successfully they are doing it. I have no knowledge at this point in time for the last 5 years or so, but when I had opportunity of exploring the manufacture process of this plant, it was at 100%. Now it is saying that they are going to become carbon neutral by 2015, and they have already charted out a plan. Majority of the waste that they handle and utilize is plastic waste. You have ArcelorMittal, which is also announced that they will use hydrogen as a fuel, and also you know, a different you know, approach called smart carbon in steel making to achieve the carbon neutrality by 2015. There are several steel plants, you know, in the country and abroad, who are all evaluating different options for greening the industry using various options, including the, you know, use of scrap steel as an input material, because then you are reducing the manufacturing CO2 generation, which is happening otherwise. What are the feasible materials for use as secondary resources in blast furnaces? For example, you know, plastic waste, RDF, SRF, spent solvents from chemical industry, waste oils, tank bottom sludges, tank bottom oils, biomass from agricultural activities, charcoal made from agricultural substrates, spent carbon, carbon black from pyrolysis industry, bamboo and other energy plantations, pyrolysis oil, forest felling, harvest residues, crop residues, green hydrogen produced by green electricity, green hydrogen produced from biomass, gasification of industrial waste. These are all avenues which are available for steel industry. It is not as versatile as cement, in terms of manufacture to utilize all kinds of hazardous, non-hazardous, with, without ash, etc. But it has also got a lot of opportunity to do it. And the industry is very, very positively looking at utilizing. Whether these secondary materials, which are going to be utilized, are they available? If you look at our country itself, large quantum of plastic waste is available from paper manufacturing, which is happening in state like Gujarat. There are already two cement plants, two power plants which have come on based on this. There's large amount of plastic waste, cement industry is utilizing from it, but still there is a lot. So steel plants can utilize that. Supply chain needs to be built to put in place to ensure that RDF from towns and cities can be moved to the steel plants. Torrefication of plastic waste into coal, which is called as charcoal. So if that is done, that can also be utilized. Sourcing of post-harvest biomass, groundnut stems, shells, other biomass, forest felling, etc., converting that into some kind of a granule and then utilizing it as a fuel source in steel plant. Energy plantations, like paper industry has gone ahead and set up its own plantations. You can also set up your own energy plantation and then utilize that as green energy. So in power sector, the limitation is still further because of the technology which is prevailing in the thermal power plants. So here whether you have option of utilizing plastic waste, RDF, and biomass. The utilization possibility of industrial hazardous and non-hazardous waste seems little difficult. I am not saying it cannot be used. It probably can be, but it has to be proven. I have not seen or read any document evaluations to say that it is safe to do that. But that doesn't mean that it cannot be. You can always do the research and find out. And already, as I said, that solid waste management rules have said 5% substitution is feasible and should be done by anybody who is using fossil fuel. Thermal power plants are one. So if they start utilizing this material, large amount of waste which we are seeing around can also be dealt with in a very, very sustainable manner. So what needs to be done for decarbonization to happen? One is we have to target waste as a resource, and then we have to convert waste into resource. If it is already demonstrated resource for utilization in your industry, then you must go ahead with it. Otherwise, you should demonstrate it through a trial that cement industry did, 90 trials of all kinds of material from simple to complex. And then once it is accepted as a technology, as a technology option for sustainable management of this waste, then you start commercial use of this particular waste stream. The key factor in the entire thing, because you are utilizing waste as a resource, is the quality assessment and quality control. In fact, the first capex that we spent while starting to utilize the waste material was laboratories. We spent 8 crore rupees in ACC. That was the first capex where we said we need 4 laboratories in 4 different corners of in the country and start understanding the waste material as to what they are, what do they contain, what is it that is acceptable and what is it that is not acceptable into that. And that's a process which actually determines how we are going to use it. And in the manufacturing sector, there's a huge opportunity for the circularity to happen. I'm giving some brief insight into this. You have C&D waste, you can convert that into sand and aggregates, you can start utilizing. You have RDF, you utilize it as fuel and cement, you produce ash, ash can be converted into bricks, bricks can be utilized for cement. You have industrial hazardous, non-hazardous, again utilize it as fuel, produce cement out of it, use it for applications. You have agro waste, you use it in power plants or cement plants. You have fly ash, utilize it for manufacturing bricks or cement, use it. You have SOx emission, convert that into gypsum, utilize it as a gypsum raw material and give back to the society. you have SOx and NOx emissions together in power plant, for example, or in steel plants, or even in cement plants, you can react that with ammonia to form ammonium sulfate and ammonium nitrate fertilizer, and that can be put back as a fertilizer source. The technologies are all feasible, available also, most of them. Converting CO2 into algae, a large amount of CO2 will get sequestered, and a fuel source will get produced. CO2 can be converted into methanol by taking green hydrogen, produce methanol. You have a whole methanol chemistry which is feasible. So I think in this decarbonization journey, there's a huge opportunity which is waiting for us to tap and move the circular economy on a very big platform. There are various resources which are available in large quantities and awaiting applications. For example, red mud from aluminum industry, LD slag from steel industry, copper slag, dredged sediments, RDF from municipal solid waste, lime sludge from paper industry, plastic waste from paper recycling industry, overburden from mines, mine tailings, coal washery residues, agro waste, C&D waste. All these wastes are available. They're great resources. Only thing is we need to use them in an appropriate manner. And that's where I think if we put zero waste as the goal and put a concept that I want to achieve it, then I think there's something that is available for us to proceed. For example, the only way, I come here rather than going the whole way, the platforms and tools, if we build for waste to get identified, waste to get diverted to the appropriate, applications through a process which is called as industrial symbiosis, new products will form, new applications will form, new processes will form. For that, there'll be networks which will get developed, a lot of research activity which will be happening across the boundaries of the industry sectors, and something new will start happening, a new economy will emerge. And that's where I think the whole game is, because cement industry had never looked at industry, engineering industry or chemical or fertilizer or in other industries. But once this co-processing and resource utilization started, we became collaborative in entire journey, and that's what has to happen. So this concept of industrial symbiosis for circular economy is pretty unique and required to achieve zero waste. I don't want to go into details of that, but it is the emerging field as I see, and there's a big opportunity waiting for us, where converting waste into secondary resources and creating an economy for utilizing secondary resources start working. I don't want to spend more time. I think my time is coming up. Thank you very much for that, giving me this opportunity. I hope I was able to do justice to the topic and also to the time that you gave it to us, sir. I end here. If there's any question, I'll be very happy to answer, sir. Over to you, Grover, sir.
Thank you, Parlikar sir. That was a very, very interesting talk. Yes, you have taken exactly 1 hour, and it has been a very nice journey to for us to learn what you are doing. So I'm sure there are many questions from the audience, but I will start with the first 2 questions. You covered in your major part of the presentation cement industry and use of different raw materials. How does it affect properties of cement, and how the industry is controlling that? Because when different kinds of inputs are there, properties are going to be influenced. How industry is exercising control on that aspect?
Yes, sir, that's a very, very important, I think, question, and that's where the whole success lies of the cement industry. The input material, as per the guidelines or as per the practices which are woven for co-processing, you have to analyze the input material and ascertain that no poison is entering the cement kiln. Now, the particular poisons are, as I said, mercury, chromium 6, and then you have the chloride or chlorine as such, you have phosphorus, you have sulfur. These are kind of poisons in the cement manufacture, because if you don't control them at acceptable level, it causes the damage to the quality of the product that you are producing and also impacts the emission. So this particular exercise and cement industry has learned to do it now. There are also, prescription guidelines which have been published. One as best practices by various international forums like Basel Convention, or there are guidelines, GIZ and Holcim guidelines which have prescribed this, and there are also the CPCB guidelines which have been published. They also talk about what are the controls that you must exercise so that you're not going to impact the emissions or the product quality. So a laboratory, as I said in that particular slide, for quality control and quality assessment, I think is very, very crucial. Now, many of the cement plants may not have it, but they have actually learned it from industries who have established the processes. So that way, they are not actually impacted so much. But if they go into receiving materials which are not explored at all, then there could be a major cause of concern. I'll give you one very small and very interesting example, sir. I was making a stakeholder submission in one of the conferences where Pollution Control Board and also a lot other stakeholders were there. And after this presentation, someone stood up and he said, look, you said that you will also utilize obsolete pesticides as the fuel source. So I'm now worried, because pesticide is something which will remain in the cement. I'm going to construct a water tank on my house with your cement, and what if it starts leaching, and then my entire family will be impacted by that. So then I told him, look, the conditions in the cement kiln are that you cannot, manipulate them. They are required for manufacturing cement. If you change even by 50 degrees centigrade, the cement is not going to form. So none of the cement plants, tend to or dare to change the conditions. And once you put in those conditions, any which is organic, whether it is persistent organic pollutants, ozone depleting substances, complex organic materials, it gets 100% combusted without any cause of concern. And then we also have subsequently the leachability test for the cement. We also have, various other quality control measures which ensure that there's nothing which is unacceptable or cause of concern which is there in the cement. And the cement that we produce, it meets all the specifications. So that's how I think the cement industry has built the confidence of utilizing waste materials and also putting input controls.
I have a second question, but before I ask that question, I request audience to type question in the chat box or Q&A box as you find convenient. And I see one question has already come, but let me ask my question first. This municipal solid waste is something which is distributed all over the country. Apart from its pre-processing, segregating into combustible waste and pre-processing, one major issue is going to be transporting it to the site of cement plant.
Yes.
Now, how do you see this will be handled? Because the cost, if the distance involved in transportation is long, the cost can be quite prohibitive in this case.
Yes,
so
sir.
Do you expect several cement plants to come up throughout the country to tackle this municipal solid waste?
Yes, sir. Actually, this very interesting question, and I'll give you an example to answer this. In 2008, we did a trial for demonstrating plastic and RDF utilization, into cement kiln and its safety and acceptability, which was done with Indian Center for Plastics in Environment as a joint effort, and also involvement of CPCB and Ministry. That demonstrated that plastics and RDF can be very easily and appropriately utilized. Once this was demonstrated and accepted by all the stakeholders, a circular had gone from CPCB to all the states. And Goa was a state which actually was looking forward to a solution of this kind, because they didn't want to go for a landfill. They don't have land. and they didn't want to go for an incineration or any thermal treatment, which is of cause of concern because it will affect the tourist this one. So when they came to know, they said, okay, we would like to adopt this. And then they started, we had a discussion and we signed an agreement and we said we'll utilize it. The transportation distance from Goa to the plant that we had in Karnataka was 600 kilometers, right? And the cost of transportation was prohibitively high. But we said, look, we can only afford to pay what we are paying for coal and marginalized it towards the expenses that we will incur. So that's the only capability that we have. But your problem can be certainly solved if you transport it, And they started doing that. And then there was a lot of efficiency which was built into transportation. So earlier it used to cost 4,000 rupees per ton to transport. Now it is about, I think, 600 rupees or so.
Oh.
Right. And then the transportation which is happening, earlier it was only one truck, for a year or so almost, it was one truck per week. Today, sir, it is not just ACC cement plant in Karnataka, but there are several cement plants in Karnataka which are receiving waste material from Goa. And in ACC cement plant alone, it is about 300 to 400 tons a day. So, I think the market works towards that.
Yes.
And then, once the economy is there. There's another very important aspect which you raised is that, the transportation cost. The municipality also have to understand, sir, that they have a responsibility towards its disposal, and they have to allocate an expenditure towards that. They cannot expect that somebody will come and then solve this problem. So there has to be a proactive. And this example, sir, has already moved across the borders now. So there are several cement plants in the country and several municipalities in the country who have understood this particular concept, and they are collaborating with each other and sending across the waste material to the cement plants. There are different models which are working today.
Yeah, that's very good. Now I see there are 3 questions here from the audience.
Yes, sir.
The first one is from Dr. R.K. Singh.
Yes, sir.
He writes, he's requesting, he wants to know overall, how do you see the scaling up of the presented technologies for achieving decarbonization during the next 3 decades as required?
Sure. The decarbonization using the co-processing technology, I'll answer first the cement sector. So it is a learning process and also infrastructure driven process, because you have to set up facilities to meet the requirements of the co-processing. For example, if you have to co-process 10 tons per day, you need to set up 10 tons per day facility. If you want 100 tons per day co-processing, you have to set up 100 tons per day, and 1,000 tons per day is 1,000 tons per day. Now, this investment obviously cannot be 1,000 tons per day in one go, because the viability won't be there. So the cement industry scales up this particular approach in stages only. So for example, in most of the plants today, the initial investment is for, say, about maybe about 10 tons per day only. Then they scale it to 100 tons per day. And now there are several plants which are moving towards 1,000 tons per day. Now, in the process, there's learning, technology assimilation, capability building, and also in terms of the safety, in terms of storage, in terms of firefighting, everything has to be embedded into the system. And that's how the scale up happens. In terms of technology scale up or science behind that is only learning by doing. I don't think there are, defined, algorithms or processes by which you can just design a system and go ahead with it. Cement kiln itself is an art to a large extent and fuzzy kind of a technology-based system, and even utilizing waste streams also is in the same way. So you have to go through this learning process, and it all depends. There are cement kilns who have moved from these 10 tons to about 500 tons per day in a matter of 3 to 4 years, and there are some who are doing it in 1 or 2 years also. So it's, and the system also and the situation also is driving. Today the coal prices are going very high, and that's also driving the cement industry to move faster towards utilizing the waste stream. So I think that's how I would say for cement. For other sectors, of course, I think it has to move. I mean, it will take some time. It's a large learning process which is involved.
Next question is from Dr. V. N. Hegde.
Yes, sir.
Our codes permit OPC replacement with 35% fly ash and slag with 70%. When we reach a stage when OPC is completely replaced with industrial wastes?
Sir, I mean, yes, I'm sure you and me both are optimistic about that. There are materials which are having that kind of a binding properties. There are also a lot of new cements which are being worked upon, which are likely to have that kind of a situation where you don't need thermal treatment at all. You can just blend the materials and achieve the binding properties that you want, but they are all, I would say, at a very primitive stage of development. And also because if you once you decide to produce it as a binder, it has to sustain the life of that particular construction for 100 years at least. So you need a very strong evidence of what you are doing is acceptable for that kind of an application. So a lot of research is happening, I would say, and I'm, at least I as an industry professional, cement industry professional, very optimistic that this is going to happen in days to come.
And the last question is from Dr. Abhishek Bodalapati. How co-processing can help steel industry, which is heavily dependent on coal as an energy resource and also as a reducing agent?
Yeah. That's I gave an example very briefly about this Voestalpine Austria plant. So they use mainly the plastic waste as a fuel source. Now, in countries of that kind, Europe, etc., the recycling of plastics is very limited. It's not to an extent like it happens in our country. So therefore, they probably will be they have been able to afford and utilize all kinds of plastic waste which is coming. But in our country, the plastic utilization is growing, and plastic waste generation also is increasing. This large amount of plastic waste which is there is one source for the blast furnace, industries or steel industry to utilize it. The temperature conditions in the blast furnace are also almost similar to that of steel or that of cement. So even there, the hazardous waste materials or the non-hazardous waste materials from industry can be utilized. There are no demonstrated, publications or trials with which, this can be confidently done or will be allowed or permitted to do. So I think the steel industry has to move forward by taking trials, as cement industry did in the country, demonstrating that, yes, my industry also is in a position to utilize that. And I will demonstrate there's no cause of concern from emission or the product that I'm manufacturing. And I think that's how the gates will start opening up. In fact, first time when CPCB wanted that co-processing should come into the country, they brought out the guidelines in 2010, where it was the heading was the guidelines for co-processing in steel, in cement, steel and power. So the government is already geared up, to move the cement industry, the steel and power industry towards the alternative fuels. So here, I think there's a desire, there's a willingness which has to come from the industry. They have to demonstrate that yes, it is feasible, sustainable, manageable, to utilize this waste. And we would like to go ahead, demonstrate that, get the stakeholder confidence, and then move ahead. I think that is what is required to be done by the steel industry.
Well, I wanted to finish by 6:30, but there are questions, so I think you don't mind going ahead and.
No problem, sir. I'll be
responding to
very
those
happy.
questions.
I'll be very happy. No problem.
Dr. Rahul Gundre is asking, is it possible to transport biomass also similar to MSW?
Yes, sir. No, very much so. Biomass also can be, transported across distances. You can pelletize it so that the transportation cost can be reduced. You can, you can process it along with other materials. For example, industrial hazardous materials or other materials, plastic materials. You can put them together. See, there is no requirement that biomass has to move only biomass.
Yes,
if it is going to bring economic in transportation, in fact, I had a desire that, for example, a place like Mumbai, where the cement plant is not very near, it's almost 800 kilometers away, in the Nagpur and Chandrapur belt. So can we take hazardous material, which comes with gate fee for disposal? So it's a money which comes along with the material, and this material like RDF, together can be transported and bring economy in the transportation, and then transport it. So there are ways in which this will have to be worked out, and a new thought process, and systems will have to be put in place. Then it is possible. This large amount of pareli which is being burnt in Punjab, Haryana, I'm sure it can be moved by doing processing. We don't want to do it, in that manner, or we have not thought of doing, I would say. But I am saying today, there are many companies who are taking leads and at least are able to transport it to Rajasthan, to the cement plants. And a good way things are starting. There are cement plants which are tying up with such agencies who are taking out this pareli and then converting that into granules or baling them properly, intensifying them and sending it across to cement plants. So move is started there. I'm very hopeful that things will happen very soon.
Next question is again from Rahul.
Yes, sir.
Why large amount of red mud is not utilized? 100% for producing composite cement.
That's a very good question. Actually, the red mud as such is utilized in the cement manufacture as a iron substitute, because it has got almost about 50% iron content in that, and rest all is silica, alumina, etc., etc. On its own, like fly ash or slag, it does not have pozzolanic properties, so that it can just blend it into the cement. There are technologies which have been researched at bench scale, where the red mud is subjected to certain temperature and conditions to derive these pozzolanic properties. So if the red mud is converted into a pozzolanic material, then maybe 20% or 30% composition of OPC and red mud can be produced as a new cement like fly ash and slag. Today, it is only 1% or 2% which is getting into the cement, because it is only iron substitute. So that is why this 100% utilization of red mud is not happening. Interesting thing is, sir, that 1 ton of aluminum produces almost 3 tons of red mud. So we produce about 3 million tons of aluminum in the country. We produce 10 million tons of red mud. Whereas utilization, as I said, is about 0.5 million tons only. And that is because it is only 1% or so replacement of iron which is happening. But if we produce it, convert it into the pozzolanic material through a technology intervention, yes, it is possible, large quantity. There's another angle, that it is not just cement where the red mud can be utilized. It can be utilized into the construction also. And that is where, this can be converted into sand and can be utilized as a sand substitute. Now, there's again technological intervention which is required. And unfortunately, industry is not looking at it, sir. In fact, I had an opportunity of doing this study under a European Union assignment where whether red mud, 100% of India's red mud can be utilized in the cement and construction sector. And my outcome of the study was, yes, it can be, provided, we give a certain appropriate direction towards this assessment. And both these sectors will consume almost everything which is getting generated in the country. That's the state of affairs.
I see your lecture has generated a lot of interest, but I'm going to take only two more questions, and since they are related, I'll read both of them.
Yes, sir.
To answer that. Mr. Sanat Kumar is asking, is the energy used in the pre-processing step accounted for in the total energy required in cement manufacture?
Yes.
Is it a high proportion? Then he continues, combusting PVC material may release chlorine, which you do not want. And Mr. Ramesh Jaipriya is asking, what is the way forward to solving the burning issues of plastics that we have got?
Sure.
So take up both of them, and then we'll stop here.
Sure, sir. So first thing is, I'll address the PVC concern, because that's a big mindset around PVC, that it has got chlorine, and therefore there would be cause of emissions of dioxins and furans. So yes, thermal treatment of PVC or any organic material containing chlorine is amenable for dioxin furan emissions. But dioxin furan emissions happen under certain conditions only, which is low temperature and also longer residence times. Now in cement kiln, we do not have that kind of a condition at all. Whether the chlorine in PVC, which is an organic chlorine, or whether it is a calcium chloride chlorine, which is an inorganic chlorine, for cement kiln, both these chlorines are same. It's not different. So we limit the chlorine input into the cement kiln to only an acceptable level, which is defined by the science of cement manufacture. And it is very clearly understood. And if there is something more which is getting into the cement kiln, you have to take it out of the cement kiln through a process which is called as chlorine bypass. So therefore, chlorine, whether it is from PVC or otherwise, is not a cause of concern. That is technical answer for this. But the most important aspect is PVC does not get into the waste stream. It's an engineering plastic, and this material finds use in its recycling processes substantially. There are many, the pipes for agricultural purposes which are made utilizing recycling PVC, and it fetches much more price for this waste material than maybe the cement kiln will be able to afford it. Second is in context in relation to the plastic waste. All kinds of plastic waste are feasible to be utilized in cement kiln. There is only an economic consideration that has to be looked at. The cement kilns or plants have a certain cost of thermal treatment, which is by way of coal utilization. So long as the plastic are getting delivered at the plant at a price cheaper or equal to, or whatever cement plants feel is right, then the plastic utilization happens without any cause of concern. The number of, that I talked about 0.5 million tons of plastic waste is getting utilized today in cement manufacture is only because of the business model which is surviving there. Entire plastic waste, as I said, from Goa, it goes into the cement kilns of Karnataka because there's a business model which has been arrived at, where the collaboration between the waste generator and cement kiln is appropriately happening with full transparency between them, that other one is not making money or other one is not getting exploited. I think that is what is required to happen for utilization of plastic waste. There are cases where the transportation distance is very high. I think, I have been advocating with the government that you must subsidize that. Then the solution will happen, because otherwise why cement plant will subsidize? It's not likely. So government can always subsidize, if it needs to be, right, like the way they subsidize the fertilizer for the municipal solid waste. So that is the state of affairs. The last thing I forgot, sir, what you asked about.
is the energy used in the pre-processing step
Yeah.
accounted for in the total energy
Correct.
required in cement manufacture?
Yes, that's a very important. Yes, sir. That's a very important question. You know, what happens is the coal substitution that we talk about with the fossil fuel, there are various angles with which it has to be looked at. Coal is a dry material. It doesn't have moisture, whereas waste materials have got substantial moisture. So this moisture also has to be driven away, you know, in the cement manufacturing stage. So that requires energy. So there is a allocation of that energy or consideration of that energy in cement manufacture. Pre-processing. So while pre-processing also we need to do a lot of effort in terms of using either electrical energy for shredding, blending, you know, transporting, etc., or they can be some processes where, you know, we have to remove that particular moisture, like drying process. So that energy also is required. Finally, the cement plant will be able to utilize this waste material as resource when it is cheaper than or equal to the cost of coal that it is replacing. So all the energy have to be configured in the calculation, whether it is at pre-processing or inherent because of moisture or, you know, lower combustibility of the material, etc., in the process of calculation, and then only, you know, the justice to the utilization has to be done. So very much true, it has to be done in that manner and is accounted in the cement industry.
Yes, I see that still one or two more questions are there, but I have to stop it here.
Yes,
and thank you very much. I request Dr. Saraswati Rai to a vote of thanks now. Dr. Saraswati, you are there?
Yes, sir. Yes,
Yeah.
I'm there. Am I audible?
yes,
Yes, you are audible. Yes.
Yeah, thanks a lot. I'm sorry for my delayed joining. It was wonderful to listen to Ulhas, and I don't know how much trouble he has taken because he has just recently shifted his residence from Mumbai to Bangalore, so he was very busy in doing that. Still, he has accepted our request and delivered this fantastic lecture. And it was really nice to see that he is able to take care of all these questions and very lively discussions he could conduct. So thanks again. I also thank to the audience who all took part in these lively discussions and listened to this lecture. We thank INAE for doing all this efforts on putting all the supports for conducting this webinar, especially Colonel Rai and his teammates for informing to the fellowships and doing all these transmission arrangements. So thanks again. I also thank Dr. Grover because I know how busy he was today. Still, he could make it and conduct this webinar. And thank you all others, all our team members. DP Mishra Sahab, because he only introduced me to Parlikar, and all others. Thank you very much. And I think we'll be again back in the month of December with one more interesting topic. This topic was of very much practical importance. And I think those who are practicing engineers must have learned a lot from this. Similar way, we will try to get some more good topics. Thank you. Thank you, everybody.
Thank you very much, sir.
Thank you. Thank you, Parlikar.
It was a pleasure. Thank you, sir.
Very good talk.
Thank you. Bye.
Bye.
So we can close now. Professor Suresh, you want to say something?
Yeah, Suresh also, yeah.
You are muted, sir. You are muted, sir.
I just wanted to thank Mr. Parlikar for the lecture and for taking time out to speak to us today. Thank you very much.
Thank you, sir.
Thank you, everybody.
Okay.
Okay.
Good night.